is starting to become outdated as a definition because they've been very surprised. Rice University does a lot of nanotechnology stuff. And the woman over there said we were very surprised when we first started seeing the melting points were different. Some of the properties were totally different when you get down to that size. So hang on to this for the time being until our book is updated. But just to open your mind that science is always changing, so we've got to be flexible to new ways of thinking about this stuff. Okay, so that's atom and how we'll use it. Then, subatomic particles. And I'd like to spend some time on this more than your chapter does here, but it's going to save us time down the road. And let's talk about subatomic particles. Okay, let's analyze that word. Atom, of course, we're talking about elements. Sub meaning little particles that go to make up the atom. And we're going to consider three. If you go on and take nuclear physics and go into that area, you're going to find they believe now there's something like 200 or so different subatomic particles. We're not going to burden ourselves with all of that, but we're going to talk about three. Could anybody tell me one? Do you remember this from way back? Neutrons. Okay, now we're on a roll. Neutrons, and we abbreviate that with an N. And what else did I hear? Protons. Good. We abbreviate that with a small p. What's the third type? Electrons. Good. And we abbreviate that with a small e, and we almost always put a negative sign with that, which implies the charge. Now, I want to make up a table, and we're going to talk about the mass, you know, how much matter something has, and also the charge. Excuse me. If we could take a proton and actually go weigh it and find its mass, we would find it weighs something times 10 to the minus 24 grams. I mean, we are talking small. A gram already is pretty small. Here, if I move this off. How many grams do you think that is? Give me a number. A few? A few? You don't want to say? You don't want me to pin you down? How many grams do you think that ring is? 100. 100 grams?
50 grams.
50 grams? At least you're not sheep. You all think for yourself. 75? I think it's less than 10, actually. We can weigh it when we get down the hall. The point is, if you've grown up here in the system of the English system, we don't know grams. I mean, we don't know metric, and we can't guess. You know, if you were in Europe and somebody took your purse or your bag, and the police want a description, could you tell them what that adult male? I'm assuming the wrong's male. That's sexist, but could you tell them, you know, how much they weigh in kilograms? I bet you couldn't get anywhere near. You couldn't say how tall they were in meters or centimeters, I'll bet. You couldn't guess if you grew up with the English system. You know, but if you grew up with the English system, you say, hey, the guy weighed about 150 pounds, he's 6'2". You know, you have a feel for the English system. So anyway, if you actually could weigh a proton, let's get back to the story. It would actually weigh something times 10 to the minus 24th grams. Now think about that. If I didn't lose count, and I may have lost a zero somewhere there. Small, the point is small. Okay, somebody had the brilliant idea is let's not use the real mass, let's use relative mass and make life a lot easier for everybody. So they chose to use the carbon atom as the basis. And you don't have to know why. Well, you choose carbon just because it's cheap, it's abundant. It weighs 12. Just accept that on faith. It weighs 12 in this new relative scale, atomic mass unit, AMU. Okay, if the carbon weighs 12, then I've got a proton. I've got a carbon here. I know it's 12. I take a proton in my other hand. It weighs 1/12 as much. So on this new scale, it's going to weigh 1 atomic mass unit. So it means it weighs 1/12 of what an entire carbon atom. So it's atomic mass units, relative scale, and we give it a 1 spot. Let me give you an everyday example. What if in here, I wanted to know what everybody weighed. Now, I'm really not going to ask you, so you don't think how much you're going to lie. Because in this country, women lie about their weight, men lie about their height. I mean, that's just broad generalizations, but that's usually what happens. Okay, let's say we don't want to say pounds or kilograms. We want a new relative scale. So I'm going to take her, just to make the math easy, let's say she weighs, on the old scale, exactly 100 pounds. Okay? So I'm going to make her a 1. She's a 1-person unit, 1 PU. Okay, 1-person unit. Okay, let's say he weighs, pardon me, but 200.
More than that.
Oh, really?
Oh, yeah.
I would have
We'll
guessed.
keep it even.
Okay, keep it even. Keep the math easy. Okay, on the old scale, he weighs 200 pounds. What is he on this relative scale? A 2-person unit. And we have somebody come visit us from the Texans, and they weigh 300 on the old scale. They're a 3-person unit. That's how a relative scale works. You pick your basis and compare to it. Okay, now we have a child walking down the hall. Okay, looking for his parent or her parent. Weighs 50 pounds. Looks in here to see if mom's here. Escaped from the child care over on the other side campus. Okay, the kid weighs 50 pounds. What is it on the new person unit? A half, or 0.5. That's what they did here. These are relative. And so it's a 1 AMU. And then they compared a neutron to a proton and found it's basically the same, so it's going to be a 1 as well. And then they compared an electron, and they said, hey, it's about 0. It's actually, I think, 1/2000 or something like that of a proton. They say, hey, that's so small, we're going to ignore it. And we're going to say it's 0. But if you think about electrons as particles, got to have some mass. Now, later in this book, we're going to talk about the duality of nature. And electrons have particle characteristics. They also have wave characteristics, just like physicists talk about light as being bundles of light or wavelengths of light. But that's not your concern right now. If you think of an electron as a particle, it's got to weigh something, right? But it's so small, we say it's essentially 0. Let me give you another crazy story, everyday life, to help you remember that idea. Okay, a few years ago I had a cat named George, a female cat. I named her George to make her tough. Okay, so I got this cat George, and she had a tendency to gain weight. And so I would weigh her from time to time, and I weighed her by difference. You know, you can't get a cat to stand on the bathroom scales, okay? So what I would do, of course, is I would weigh myself, I would pick up George, and I would weigh George, and I go, oh, George. You know, you subtract, of course. Okay, I said, George, you've gained weight again, you're going on a diet, no more tuna for a few days, the hard stuff only. Okay, George goes, it's fantasy time. George says, no, I haven't gained weight, I just have a whole bunch of fleas today. Well, no, I'm not buying that story, because George could have had 200 fleas on her, and a flea weighs so little, that wouldn't make George appear to be overweight. Okay, so we say the flea compared to the cat or a dog, if you're a dog person, weighs so little, we'll take it essentially as 0. Okay, so if you've gotten the analogy, the electrons are the fleas on the atom. They weigh a little something, but they don't contribute much at all. We also used a relative scale for charge. The charge of a proton is +1. Charge of a neutron, you could probably guess if you don't remember, neutrons are neutral, no charge at all. And then electrons, you could probably guess from here, -1. Okay, so need to know masses of each subatomic particle, charge of each subatomic particle. Okay, so where are we on this outline? We're right here in subatomic particles. Now, when we write an element down, from the periodic table. For instance, let me take Ag, and of course Ag is what? Helium. And I'm going to take the numbers off the periodic table. If you spot helium, it's in this upper right-hand corner. And we do things weird for a reason. Okay, the atomic number is up here in this upper right-hand corner when it's on the periodic table. Atomic number. Okay, and notice if you go through a periodic table, hydrogen is atomic number 1, helium is 2, lithium's 3, beryllium's 4, and so forth. And they're roughly in numerical order, although some weird stuff starts happening down in here. Okay, so that's your atomic number. When we write it on the board, though, or on a piece of paper, you put the atomic number in the lower left-hand corner. And this is by custom. So atomic number is down there. Okay, and then this number up here that we put in the upper left-hand corner is atomic mass. Or you'll also hear people say atomic weight, because we're real sloppy in our talk and we interchange mass and weight all the time. So we put it up there, but if you look, let's take a look at helium up here. Atomic number is in the upper right-hand corner. Mass is down here, and I'm rounding that off to the nearest whole number. So that's the atomic mass down here at the bottom. Okay, what does this tell us? A tremendous amount. The atomic number is equal to the number of protons. Number of protons. Then atomic mass is equal to protons plus neutrons. Because what contributes to the mass? If you go back here, only the protons and neutrons contribute to the mass. So the atomic mass is the sum of the two. Okay, so what can we do with this?
Figure out how many neutrons there are.
You can figure out everything. If you got a periodic table, and you will always have one, even on test day, I will give you a copy of the periodic table in case you can't see that real well or you're too vain to wear your glasses. So, or if you're in a back corner. So you'll have your own private periodic table that I will supply. You'll always have this information. And so what we can do, we could do a table. I have helium. And I can talk about protons, neutrons, electrons. I can also talk about positive charge, negative charge, and net charge. And fill out a big table for this. Okay, now I could have made the table even bigger by saying, and what's the atomic number and what is the atomic weight? But we've got it right there. So, for helium, how many protons do we have? Anybody? 2. And you get that right here. Okay? Then, for helium, how many neutrons do I have? 2. How do you get that? You subtract this from that. Okay, that's why we do stuff differently than up there on the periodic table, because for most people, when you subtract, you want the bigger number on top, and then you can just say, I need neutrons. Subtract. And we get 2 in this case. These numbers do not have to be the same. It's just you take the difference. Okay, now, the part you haven't heard about from me yet. If this is a neutral atom, meaning carrying no net charge, you know it's neutral because there's no charge showing in the upper right-hand corner. It is neutral. If it is neutral, every time you have a proton, we're going to have an electron to balance out the charge. So this means we have 2 electrons for helium. Although this info tells you right off how many protons, subtract and you get number of neutrons, and then you have to reason, it's neutral, therefore every time I have a proton, I've got to have an electron.